All right, guys, so we are still in Unit 7, where we've obviously been talking a lot about radical functions. We're also going to, in this unit, talk about, starting today, what are called inverse functions. And the reason being that inverses are somewhat important for radicals in the way that radicals relate to quadratics, even more so for what we're going to be doing moving forward in our next unit, which we will start to look at most likely after spring break, which is exponential and logarithmic functions, and how those two functions are inverses. In fact, we'll even talk a little bit about that in this unit as well. So let's go back to Unit 1, where we first started to talk about inverse functions. And we didn't get too far in depth with them. Again, if you remember, Unit 1 was kind of just the advertisement for everything else we were going to be doing. It was just kind of the very most basic stuff. But we did talk about what was called the vertical line test and horizontal line test. And so when you're looking at this relation, which is our linear graph that we've got for example A, first of all, is the original relation a function? In other words, does it pass the vertical line test? Meaning, if I draw a vertical line through this function, is there anywhere that it would cross through more than once? And in fact, the answer is no. And that's a good thing. Remember that does, in fact, mean that it passes the vertical line test. Now, to decide if the inverse is a function, we do something similar. We draw a horizontal line, however, and we ask the same question. Is there anywhere that this horizontal line would pass through our function or our relation more than once? And in fact, the answer is also no, which is also a good thing. That means that yes, it does in fact pass the horizontal line test. If it were to ever cross through in more than one place, we would have to say that the answer was no, that it failed either the vertical line test or the horizontal line test, depending on which direction you were looking at. All right, so as a warm-up, let's also go back and remind ourselves of what exactly an inverse does. Before we do that, let's just go ahead and fill in this table. So we've got our function where it says g of x is equal to 5x plus 3, and is wanting us to fill in those values for some values of x. So remember, all you need to do there is take negative 2, put it in for x, so that would be 5 multiplied by negative 2 plus 3. And when you simplify that, you get negative 10 plus 3 is negative 7. So there would be the y value. We'll continue to do that for each of our x values. So if you put in negative 1 for x in our function, then we get negative 5 plus 3 is negative 2. If we put 0 into our function, we get 0 plus 3, which is 3, not 0. And again, since our slope is 5 up here, we should also notice that each of our values are going up by 5, which could make filling in these last two blanks a little bit easier if we continue to do that, which is 8 and 13. If you didn't quite pick up on that, then obviously just continue plugging in values for x, and you should get those values that way as well. But here is the idea of an inverse. When we are asked to evaluate something like g inverse of negative 2, that does not mean take negative 2 and put it in for x and see what you get. That is not what that is saying. The inverse says to go the other direction. Find the output of negative 2 and write down what the input was that gave it to you. So g inverse of negative 2 takes the output of negative 2 and gives you the input, which is negative 1. So let's do a couple more of those. G inverse of 3. 3 came from an input of 0. So there would be our answer for that particular problem. And g inverse of 13, 13 came from 2. So that would be our answer for that expression. Now, obviously, for a simple example like this, that's not too bad. However, what if we wanted to find g inverse for any number? So if we wanted g inverse of 27 or g inverse of 4, how would we find what that value of x was? Well, a table's not going to cut it. We're going to have something else to be more helpful. And that's going to be the idea of what's an inverse of a function. So rather than just filling out a table, what if we want an actual function that's the inverse? In other words, another function separate from the original one, which would take you from an output back to an input. In fact, that's the very definition of the inverse of a function. It is a function which relates the outputs of some other function to their inputs. So it's a pretty simple idea. The actual execution of finding the inverse, though, can be somewhat difficult at times. It really does test your ability to solve equations. So again, the inverse of a function is a function which relates the outputs of some other function to their inputs. In other words, we're not going to have to necessarily use a table. We're going to have an actual function that we can use. So let's talk about your step-by-steps. How exactly are we going to go about finding an inverse function? Well, step number one is we need to replace f of x with y. So if it's written as a function, or if it's an equation already, you might be able to skip this step. But we're going to replace the function notation f of x with the variable y. Now, a lot of times those can be used interchangeably. The f of x is, though, particular to a function, whereas y can just be for any equation. Step number two is we're going to try to solve for x. So whatever our input is, we're going to try to solve for that. Step number three is we're going to swap x and y. So once we've solved for x, x and y are going to swap places, which essentially is going to then make your x, which was your inputs, your outputs, and vice versa. That's where you truly get your inverse function. And so in step four, we've got our inverse function. We just need to call it a function. So now we're going to replace y with f inverse of x. And obviously, if it's g of x, then replace f with g. If it was h of x, then use that instead of f of x. So this is more so just for general use. Obviously, this works for any function, not just f. All right, well, let's do some practice with that. And we're going to start with just some very basic equations. In fact, we're going to start by just looking at linear equations first, since those are probably the easiest to solve for a variable n. And then we'll take a look at some of the more complicated cases. Okay, so for our first few examples, for a, b, and c, you're going to start with just an equation, which means we can kind of skip that first step of replacing f of x with y. So step number two said that we're going to try to solve for x. So on example A, if we're going to solve for x, we'll start by subtracting 3 from both sides. On the left side, that'll be y minus 3 is equal to 2x. And now to get x by itself, divide both sides by 2, and we'll get that y minus 3 over 2 is equal to x. So now let's go ahead and do step 3. Now that we've got x by itself, we're going to swap x and y. So now we're going to have the x minus 3 over 2 is equal to y. And at that point, we're done. It was not written as a function in the first place, so we aren't going to bother with writing it as one and now, but that would be our last step, and in fact, we'll look at that in a few examples. So here's what that inverse does. If you're kind of curious, why are we doing this? Let's say you put in the number 1 for x. Well, if that's the case, then our y value that we would have gotten would have been 2 multiplied by 1 plus 3, which is 5. Now let's say we wanted to not know the number we got out of it, but the number we put into it. So what if we knew that we got a 5, but we wanted to know what was the x value? Well, if you take 5 and put it into our inverse equation, then 5 minus 3 over 2 becomes 2 over 2, which is 1. That tells you that if you had 5 as your output, then 1 had to be your input, which in fact was the case. So that is the idea of our inverse function, is that we're able to actually take the outputs for our function and get the inputs that they would have come from. All right, so let's go ahead and do a couple more examples of this working with just equations, and then we'll look at it with functions. So on the second equation, we've got y equals 3x minus 1. So again, step number 2 is where we will start, which is solving for x. So we'll have y plus 1 is equal to 3x. So divide both sides by 3, and you get that y plus 1 over 3 is equal to x. Now comes step 3, swap x and y. So x plus 1 over 3 is equal to y. And since it wasn't written as a function in the first place, we'll just leave it as the inverse equation. So there is going to be a difference between the inverse equation and the inverse function. All right, for this last example for C, pretty easy one to figure out. To solve for x, just add 2 to both sides. That gives you y plus 2 is equal to x. Now swap x and y. So x plus 2 is equal to y, and there's our inverse equation. Which this one, in fact, should be pretty easy and pretty straightforward to think about. If for the original equation you're subtracting 2, then the inverse, the opposite of that, would be to take everything and add by 2. So again, single operation, that should be pretty straightforward. Okay, so let's look at it in the context of functions now. So here's where we're going to have some additional steps. Really should not be too difficult though. So for example D, step number 1 is that we're going to replace f of x with y. So we'll say that y is equal to 2x. Step number 2, we'll solve for x. So divide both sides by 2. That'll give you y over 2 is equal to x. Step number 3, swap x and y. So x over 2 is equal to y. And then step number 4, replace y with f inverse of x. So now we are actually calling it the inverse function. The rest of it stays the same. I'll just write that on the right side of the function rather than the left side. So our inverse function, f inverse of x, is x over 2. Which, again, single operation should kind of make sense. If your original function takes all of your inputs and multiplies them by 2, then to get back to your inputs, take all your outputs, divide them by 2, and we should be back to our original inputs. So again, for a single operation, should be pretty straightforward. All right. Let's take a look at example E. So in example E, we're going to start the exact same way. Replace f of x with y. So y is equal to negative x plus 1. Step number 2, we're going to solve for x. So we'll start by subtracting 1 from both sides. That will be y minus 1 is equal to negative x. And then to get x by itself, either multiply or divide by negative 1 on both sides. That's going to essentially change the signs of everything in your equation to where now you'll have the negative y plus 1 is equal to x. At this point, we just need to swap x and y. So that would be that negative x plus 1 is equal to y. And now we will do the final step, which is to replace y with f inverse of x. And then our inverse equation is negative x plus 1. So kind of a interesting example here. Our inverse actually ended up being the exact same equation as the original one. So kind of an interesting one to look at. All right, last one that we will look at, f of x equals 1/3 x minus 2. So let's go ahead and solve for our inverse. Step number 1, replace f of x with y. Step number 2, let's solve for x. So let's add 2 to both sides. So y plus 2 is equal to 1/3 x. And then to get x by itself, take both sides and multiply by the reciprocal of your fraction. The reciprocal of 1/3 is just the number 3. And if you want to distribute, you can, but don't have to. But 3y plus 6 is going to be equal to x. So step number 3, we're going to swap x and y. So that would be that 3x plus 6 is equal to y. And finally, step number 4, we're going to replace y with f inverse of x. And then write what that is equal to, which was 3x plus 6. And there's our inverse function. All right, so a quick note about functions and their inverses when they are graphed together. Well, let's just kind of talk about this and then we'll look at some of the graphs and some of the examples here. So when we graph a function and its inverse together, they should be symmetrical about a particular line. They're going to be symmetrical about the line y equals x. So let's go ahead and see if that's really the case. So we're going to use Desmos in order to do that. We're going to graph our functions together in pairs to kind of see what exactly is going on as far as the function and its inverse go. So our first example, we've got f of x is equal to 4x plus 3. G of x is equal to x minus 3 over 4. Let's go to Desmos now and see what that looks like. So again, the first function was 4x plus 3. The second function was x minus 3 over 4. And let's go ahead and do this. I'm going to graph the line y equals x and put that in dotted lines so we can look and see, does it look like our two functions are symmetrical about that line? In other words, if you were to reflect this top half of them over the line to get this bottom half, would they look the same? And in fact, they do. So it looks like those are good. So let's look at our next pair of functions. So if you want to go back to the notes, you can. I'll go ahead and I've got them pulled up separately, so I'm going to go ahead and graph them right now. The first of which is x cubed plus 1. And the second of which is the cube root, which you'll have to, if you're using Desmos, go to functions, pick this in, and then the square root sign, type in the 3, and then x minus 1. Oops. And here is the other function. And once again, it does look as though they are inverses of each other. And it should kind of make sense, especially if you look at the main part of the equation. The first one is being cubed. The second one is taking the cube root of a number. So those are inverses. One you're adding by one you're subtracting by 1. So it does kind of make sense that they would be inverses. And in fact, looking at the graph, you can definitely see the symmetry about that line y equals x. Okay, let's look at our third pair of functions. So our first function was the square root of x minus 3. The second was x squared plus 3. So here are those two functions. And this is not the case. It looks as though something's going on to where we're not quite the same. And if you notice why that is, it looks like we're missing part of one of our inverses. In fact, that square root of x minus 3, which is the bottom half, you really need kind of another part to it. What you would really need is to also have a negative square root of x minus 3 as well. The problem with that, though, is notice that now it does not pass the vertical line test. If you were to try to use the vertical line test on your function on the right side of this graph, it's going to fail the vertical line test. It's not going to be a function. And so we can't necessarily have both halves of that. And so the reason why it's not working is if you look at your original function, x squared plus 3, it doesn't pass the horizontal line test. If you try to draw a horizontal line, it's going to cross through in more than one place, which is a problem. And so what we're going to have to do is we're going to have to do something with that function x squared plus 3. We're going to have to do what's called restricting the domain. In other words, rather than looking at the entire graph of x squared plus 3, what we're going to do instead is we're only going to look at where x is greater than or equal to 0. And so when we do that, and we only look at part of our function rather than the entire thing, now it does work. If you look at your graph, it is symmetrical about that line y equals x. You can go ahead and reflect over it to check and see that that is the case. And so that's going to actually be what we'll talk about for the second part of the notes, which I will be making a second video for, is what to do with a restricted domain, how to tell which half you would use. Why aren't we using the half where x is less than or equal to 0 instead? How did I know that it needed to be greater than or equal to 0? Those are all questions that we're going to look at in the second part of this section of the notes. Real quick, before we do that, let's go ahead and look at our last function, which was actually a rational function. So let me go ahead and type that in as well, and we'll check to see how it works. So the first part of this was we had 4x plus 4 in the numerator and x plus 5 in the denominator. So here was the original function. I'll zoom out a little bit so you can see that a little bit better. The inverse of that was the following function, 4 minus 5x over x minus 4. Oops, let me get that typed in correctly. There we go. So again, a little bit hard to see, but you can definitely tell where that y equals x line crosses through, and you can see that they are in fact symmetrical. A little bit hard to see because of the axes that are in there, but they do in fact reflect, and in this case, we don't have to worry about that restricted domain. So there's something about, again, that x squared, a quadratic, and that radical of x minus 3 that were different from the others. Again, that was the ones that we were going to have to talk about a restricted domain for, and that'll be what we'll look at in the second video. Until then, have a good rest of your day.